All right, so last time we introduced the notion of Stokes theorem, or the fundamental theorem of curls. And this allowed us to relate a line integral and a surface integral. So it's essentially a one-dimension higher version of Green's theorem. What it says is that if I want to take an integral over a closed contour of the boundary of a surface, partial S, of f, a vector field dotted with a displacement, dr, well, that was equal to the double integral, the surface integral, over S of the curl of that vector field dotted with the differential surface. And then, of course, from this point on, we can use stuff from last video, stuff from earlier, to evaluate those surface integrals. And this isn't mutually exclusive. You can also start with a surface integral of the curl of a vector function, go from the curl of that vector field over to the vector field by finding the potential function of sorts, and then going to find the line integral over the boundary of the surface of f dot dr using whatever type of thing you want, like the Green's theorem or fundamental theorem for line integrals or parameterizations, whichever type you like. But you can also go from a line integral that you don't know how to solve, take its curl and evaluate it as a surface integral. And we kind of have the same tools for surface integrals to evaluate them as we do for line integrals. And we'll figure out some even more tricks with the next video in the divergence theorem, which will be relating surface integrals to triple integrals, or volume integrals, which is also known as the Gauss law. So anyways, what I'd like to do now is kind of explore Stokes' theorem. So we talked about Maxwell's equations when we wanted to apply divergence and curl, and it gave us equations that found the divergence of the magnetic field, the curl of the magnetic field. Curl was in the wrong place. Don't mind that. The divergence of the electric field and the divergence of the curl of the magnetic field. So we're going to look at the curl. Obviously, our fundamental theorem here deals with curls and not divergences. That'll be the next video. But anyways, we will look at how we can change these differential forms into integral forms, or integral forms into differential forms. Because, of course, Maxwell's equations, they have the integral forms, and then they also have the differential forms, and we're going to be looking at how to transform between those two types of forms for the E and M equations. So anyways, let's start off with Faraday's law. So we're going to be dealing with Faraday's law and Ampere's law with the Maxwell correction. So Faraday's law essentially says that if I want to take the line integral of E dot dl around a bounded surface, then that is going to be equal to the negative time derivative of the surface integral of the magnetic field dotted with that surface. Okay, so this relates the electric field and the magnetic field. This is different from the Gauss's laws, which are exclusive to either the magnetic or electric field. These two curl laws, they relate them to the other field. So it shows that they're inherently related, and you solve these differential equations and you find that there are wave solutions for electromagnetic waves, right? That's how it was discovered, in fact. Anyways, I'm getting a bit of a digression here, but the main point is that we're using the Stokes theorem, which says that the contour integral of f dot dr, or in our case, E dot dl, is equal to the surface integral over the curl of f dot ds. And that's what we're doing in this step. We're using Stokes' theorem to go from E dot dl to nabla times E dot ds. And then, of course, this is still equal to negative time derivative of that other surface integral. But now what we can do is, because the only thing that's dependent on time in this integrand here is only the B field, we can pull the partial derivative inside of the surface integral. So it doesn't matter whether we do the integral later or earlier, we can make it a partial derivative as long as it doesn't monkey around with the other things, like the x, y, z components of the B field. As long as it's only time, then we're good. That's, of course, still equal to the integral of the curl of EDS. But now guess what we can do? This is one of my favorite things to do in life. And we have the integral over any closed loop. So for all closed loops, this is true. Because for all closed loops, Faraday's law holds, what we can do is we can cancel out these integrals and cancel out these differentials. It's a really weird thing to do, but I guess we'll have to deal with it. But anyways, what we're left with is we're left with this bit, and then we're left with this bit, and then this negative sign. So what we can do is we can say that the curl of the electric field is equal to the negative time derivative of the magnetic field, okay? Now, I'm not going to get into exactly what these equations mean physically, but it is very interesting when you look at all four of Maxwell's equations. So it turns out that Maxwell's equations are a set of four equations. So you have Gauss's law for magnetism, Faraday's law, and then the Maxwell-Ampere law. And it turns out that two of those equations are actual equations of motion derived from something called a Lagrangian, which you learn about in classical mechanics. So you derive that from a Lagrangian. Lagrangian is just the kinetic minus the potential energy of the thing, and from that you plug it into these things called the Euler-Lagrange equations, which is just taking some partial derivatives, and you get the equation of motion. So two of these Maxwell equations are derived from the equations of motion, and then two of them are derived from the boundary conditions of the system. So together they describe how electric fields act. Again, super big digression. Let's move on to the Maxwell-Ampere law. This one looks a little bit more complicated, but it's the very same concept. Essentially, we are applying Stokes' theorem to the left-hand side, pulling time derivatives inside of integrals, and then canceling out integrals. So we have the integral over the surface of the magnetic field dotted with displacement, and that's equal to mu naught, which is it's either the permeability or permittivity of free space. I don't really know which one is which. It's mu naught and epsilon naught. That's why I'm not an engineer. I'd be messing those constants up all the time. But anyways, you have mu naught times all of this integral stuff. J here is the current density, and then ds is again the surface element. E is the electric field. Epsilon naught is the constant that we have there. Anyways, what we're going to do is we're going to apply the Stokes theorem again. So we get the double integral over S of nabla times B dot ds is equal to mu naught times the double integral of J dot ds plus E naught d dt integral of S E dot ds. Okay? So now again, what we're going to do is we're going to take this guy here and we're going to plug it, we're going to plop it inside of the derivative. We're taking the time derivative because E is the only thing that's dependent on time. We make it a partial derivative so it doesn't mess up any of the other variables we have in there. And then now we are prepared to just, with impunity, pretty much cross out all of these integrals and differential elements. And this, of course, gives us that the gradient, the curl of the magnetic field is equal to mu naught times the current density plus epsilon naught times the time derivative of the E field. So what we've determined is we've determined a way of going from the Ampere law, or the integral form of the Ampere law, to the differential form of the Ampere law. Now doing this for the from the differential form, you start with nabla times B equals mu naught J plus epsilon naught dE dt. Of course, what you just do is you just do an integral over d squared of your surface, then you do another integral over d squared of your surface, and then this is the same thing. You can use Stokes' theorem again, pull out the time derivative, then you get the integral of dl dot b is equal to the integral over your surface of mu naught times this whole business J plus epsilon naught dE dt. And then you distribute the integral out, and then you get the same thing as we have here, but in a more compact form. And then, of course, we found the Faraday law, which is that curl of E is equal to the negative time derivative of the magnetic field. So anyways, that is what I've got for today. Next video, we'll be rounding off with, I would say likely our last video for multivariable calculus, which is on the divergence theorem. Now, the divergence theorem is like the capstone of all of this. It has so many applications. all of the laws that are named after Gauss for gravity, for electromagnetism, they come from the divergence theorem. Reynolds' transport theorem, and seemingly by deduction, also the Navier-Stokes equation come as a result of the divergence theorem. So does, I believe, Poisson's equation. But they all are tributaries of the divergence theorem, and the divergence theorem is obviously a tributary of that generalized Stokes theorem that I discussed last time, that the integral over the boundary of omega of alpha is equal to the integral over omega of d alpha. Okay, and this, you can get absolutely every single one of the fundamental theorems from that fact. All right, so thanks for watching. In the next video, again, we'll be back with the divergence theorem, and we'll see you then. Thanks.